Yeah, I see we still have more audience come, so maybe we wait 1 more minute.
Sure.
Yeah, maybe I think I can start. So yeah, it's also the time. Again, thank you everyone for attending this QSR webinar, which actually our first webinar host this year. And today we are very honored to have Professor Kaibo Liu here to give us a very interesting topic. And before we start, let me just give you a brief introduction of Dr. Liu. Dr. Liu is currently a professor in Department of Industrial and System Engineering at UW-Madison and serves as associate editor of the UW-Madison IoT System Research Center. He earns his bachelor degree in IE and engineering management from Hong Kong University of Science and Technology, a master degree in statistics, and a PhD degree in industrial and engineering from Georgia Tech. Dr. Liu's research is in system informatics and big data analytics, with an emphasis on the data fusion approach for system modeling, monitoring, diagnosis, prognosis, and decision making. He is a recipient of three prestige early career awards, including the 2019 Outstanding Young Manufacturing Engineer Award by SME, the 2019 Feigelbaum Medal Award by ASQ, and the 2019 Dr. Hamd Edding Outstanding Early Career IE in Academia Award by IISE. He is also the winner of many other awards, and he is currently serving as a senior editor of IEEE TASE and the department editor of IISC Transactions on Data Science, Quality, and Reliability. Yeah, so welcome, Dr. Liu. So now it's your time. Thank you.
Thank you, Charles. And thank you everyone for attending the talk today. I'm very honored to have this opportunity to introduce the research roadmaps in my group, and also some recent advances in data science for prognostics. Okay. So I think I can skip this part since Charles has already did a very comprehensive introduction about my background. So I will start with this outline. So to begin with, I would like to first talk about what is the problems that have been studied in my research groups since I joined UW-Madison. And then I will highlight the story, how did I get started. I think the purpose for the webinar today is I want to show you the research milestone, especially how our research problem are motivated and what is the limitation after one work. And hopefully through show you this story, it can enrich your research someday in the future. And after I introduce the problem, I will mainly highlight several approaches that has been pursued in my group. The first is a health index-based approach. I selected one particular paper and go into the deep, and then I will talk about several extensions based on this foundational work. And in addition to this health index-based approach, I will also talk about other like explainable machine learning and AI models. And also, I choose one paper as a one representative work, and then I will talk about several extensions. So after that, I will further talk about one unique problem in prognostics is when we have a limited observations, but in a large heterogeneous group units. In this case, how could we conduct prognostics by using transport learning? And once we have a better prognostic results, how can we make better decision makings? So to begin with, I would like to provide you some background information first. So how can I make this smaller? It's okay. Anyway. So before I go to the deep, I would like to first give you some background information regarding the degradation. Okay. So as we know, the degradation is an inevitable process for any manufacturing and machining systems. So I started to know this field actually when I was a PhD student in Georgia Tech. That time I took a class which is offered by Professor Nagi Gabriel. And here I just borrowed the example from his lab where he used a vibration sensor try to study the rotating bearings. So as the bearing continually rotates, operates, then we will expect to see some signal like this. And once the signal reach a certain failure threshold, then the unit is regarded to fail. And in this example, this means there will be a crack occurs in the bearing and the continual growth. And that's why you expect to see a more severe vibration sensor signal. And finally, the breaks is too big. So finally the bearing breaks. But the challenges in prognostics is if we conducted these experiments for multiple times, then you will expect to see different degradation trends, and also the results in different failure time in those units. In practice, once we collected some degradation signals, then we can online predict when this unit is going to fail by incorporating the distribution of the historical failed units. More importantly, if we have more and more those sensor signal, then we can do an online Bayesian update regarding the RUL predictions. So the more information, the more accurate the prediction will be. So you can see that when we have only one degradation signal, the existing literature has already developed a very powerful tool, right? There are a lot of methodology available to conduct this prognostics. But what happens if there are multiple sensor signals? This is actually the problem has been studied since I joined Wisconsin-Madison. So in this case, some sensor may say the unit failed in a day, and some sensor may say the unit failed in a week. In this case, which sensor should we rely on? So here I want to show you a more vivid motivation example where I try to study the degradation for aircraft engines. So in this case, you can see there are different sensor measurements like a temperature, pressure, fan speeds collected from different components in this complex systems. And this data set is actually generated by this CMAP simulator. And for the researchers, students working in this field, I believe this data set is not surprising to you, right? In particular, this data set contains four subsets, which covers a different number of training units, testing units, operation condition, and also failure modes. For each training units, it operates from the beginning until finally fail. And for each testing units, it only operates for a while and then stop and before failure. And there is another file records the actual remaining lifetime for those testing units. So in this way, the practitioners can implement different algorithms and to numerically evaluate their RUL prediction results. So what are the essential challenges when we have multiple sensors and conduct prognostics? First, the data from multiple sensors are correlated, and each sensor only contains a partial information, right, regarding the degraded units. And also the different sensor may involve different sensitivity and signal to noise ratios. But that's why, in my view, there are two important challenges we need to tackle. First, we need to decide which sensor to use. Second, how do we combine and fuse those multiple relevant sensor data in order to accurately calculate the underlying health status of the units? So in the following, I will start to talk about several approaches that has been pursued in my research groups to tackling these problems. The first one is the health index-based methods. Let's see if I can include this. Okay, yeah, this is better. So in particular, I will start by highlighting this health index-based approach. And here I chose one of the representative papers, which is collaboration with my former PhD students, Changyue Song. And okay, so what do we mean by the health index-based approach? So our underlying assumption is, although we cannot directly observe the true degradation status, but we can install a lot of sensors, right? And those sensors, although they cannot directly tell the degradation, but we assume there is an unobservable metric, which we call composite health index, which can actually calculate the underlying process. And our goal is try to construct such a health index I time t by fusing those multiple sensor signal L, okay, at each time for each unit. So Z here is a fusion function and W is fusion coefficients. So if we use a simple linear fusion function as an example, then this means our health index will just be a weighted average of those multiple sensor signals. Once we constructed this health index, then we can use it for final predictions. Indeed, this health index is highly desired in practice. First, it facilitates visualizations. One of the challenges we often face when we talk with our collaborator in practice is assuming that they install the many sensors and they collect the data, and then they can visualize the degradation signal in a dashboard. But which one they should really look at? So using this approach, we can clearly tell the practitioner that the health index can actually quantify the underlying degradation status. And second, we transformed the previous challenge dealing with multiple sensors into the single sensors. So in this way, a lot of those existing methods that I have already mentioned for real-time prognostics, which apply to single sensor signal, can be directly used based on the health index. And also, this lays the foundation for the following decision-making process. Indeed, a lot of those existing literature, they actually already assumed such a health index is available when they conduct, for example, maintenance decision, scheduling, or spare parts logistics. However, how to construct this health index has not been systematically studied. So, well, now we know this health index is highly desired in practice, but from the research perspective, constructing the health index is quite challenging. This is because the true underlying degradation states is always unknown. So this means our problem is different from the classic supervised learning, where we have some response Y and we have some input X, and we want to learn the relationships. Here, recall that we only have the multiple sensor input X, but we don't have the Y, right? So this may remind some of you the terminology called unsupervised learning or semi-supervised learning, but unfortunately, this is not either. The reason is because if the health index can truly reflect the underlying degradation mechanism, then it should comply with engineering principles. So what we mean here is the health index should be monotonic. This is mainly because the degradation is an irreversible process. And second, once the health index reaches the failure threshold, the failure should occur. And also depends on what particular use cases. There may be more of those physical-based models available, which can be used to govern the behavior of the health index. And before our research, I want to emphasize that this literature still lacks of a solid analytical foundation that supports the health index-based methods. So what I mean here is, although the health index concept has been widely used, but in practice, it is in most cases, it is either assumed the health index is one of the representative degradation signal, or it is heuristically constructed by the experience of the working engineers. But no study has really shown what is the relationship, mathematical relationship between the health index and underlying degradation states. And in this work, we try to solve such a challenge. So without loss of generalities, here we consider the underlying degradation process can be characterized by such widely used mixed effect models, where the phi t is just a time covariance, so which is the same for all the units. And the gamma I here is a unique random effect parameter for each unit I. So that's why you can see this model can explain a wide range of degradation where each unit has its unique degradation trends, but they also share some commonalities. And our health index model is as follows. So we try to construct such a health index by combining those multiple sensor signals. So here I start by using a linear fusion function. And later on, I will talk about how could we extend this assumption. And such a health index will equals the underlying true degradation states plus some Y noise. Here, I want to emphasize that this Y noise is critically important. This is because our health index is constructed by fusing those multiple sensor signals. And those sensor signal contains noise, right? So there is no way for us to construct such a health index which exactly equals the underlying true. So that's why the best we can do is equals underlying true plus some Y noise. However, the underlying degradation is governed by the health index instead of governed by the underlying degradation status instead of the health index. So this means once this underlying health status reach the failure threshold, then the unit will fail. You can see that there are several parameters involved. Those including those fusion coefficients, right, to combine multiple sensors, and also those parameters related to the underlying degradation model. So to begin with, let's look at the simple case where we assume those parameters associated with the underlying degradation model are already known. And our goal is try to derive the fusion coefficients. In this case, for given a fusion coefficients, then we can combine those multiple sensor signals to construct this health index. If we know how to model the health index, then we can online predict when this unit is going to fail. So assume that we have already collected some historical failed units, right? In this way, we can compare our predicted failure time with the true failure time, okay, by using a quantile-based regression. And we can also formulate the engineering principles as constraints, those including like the failure threshold constraint or the monotonicity constraints. Or if there's any additional physical-based model, we can also add it to constrain the health index. So by minimizing this prediction error, then we can solve this health index. We can solve how this fusion coefficients and then know how to construct this health index. So this is the case when we know those degradation parameter. What happens if we do not know the underlying parameter associated with the degradation model? In this case, we can derive the unbiased estimator first. And what we can show is no matter whether we know those underlying degradation parameter, as long as we have more and more those historical units, then our derived fusion coefficients will converge to this true value. This is actually based on the convergence theory of the nonlinear quantile regression. And as I mentioned, before this study, at that time, this is the first and only work that provides such a theoretical justification of the data fusion methods for degradation modeling and prognostics. And in the following, I want to show you some quick studies. In this study, we just look at the first FD001 data sets where there is one single failure mode and one single operation conditions. But the challenge here is that each unit may associate with a different initial wear and random noise. And also there may be, and also because the underlying system is really complex, so there is no well-known physical models available. So this means we have to rely on this data-driven approach to predict this RUF. By using our proposed fusion functions, we derive the optimal weights to combine the sensors. And here is the final RUL results, where the y-axis shows the prediction error, so the smaller the better, and the x-axis shows how much information we have already collected when we conduct this prognostics. So the last line is our developed health index, and the other lines are either the prediction based on original sensor or based on some heuristic health index approach. And you can see that by using our developed health index approach, finally we can improve more than 64% compared with the best single sensor, and also improve more than 20% compared with the existing health index-based method. Here, I have an illustration to show you how could we use the health index in practice to conduct prognostics for these infill units. So here we plotted the degradation signals collected from multiple sensors, and the last one is our constructed health index from infill units. So you can see that as we collect more and more those sensor signal in real time, then we can online construct this health index. And then we can further update the prognostic models. So the more the information we have, the more accurate our prediction will be. Okay. So you can see that in this work, we have laid really solid analytical foundations, right, for the data fusion model for prognostics. After that, another question came to my mind is what happens if those data during fusion contains noise, right? Which is quite common because not all of the sensors are relevant to the underlying degradation mechanism. So this motivates us to develop a sensor selection procedure during this data fusion process. So to address this issue, we further developed efficient algorithms for BLUE during the health index construction. So what I mean here is our derived fusion coefficients will have the smallest variance among all those that are unbiased and also linear. Okay, and in this way, we can impose the sensor selection through this adaptive lasso algorithms when deriving the fusion coefficients. Here we use adaptive lasso is mainly because it's oracle properties. And here shows the numerical performance when we compare these new algorithms with the previous one that I talked about based on the pointwise regression. So you can see that once we impose these sensor selection schemes during the fusion, so we can further improve the RUR prediction results. So far, we talk about these linear fusion functions. So the next questions after this we realize is in practice, those sensors may have highly nonlinear relationships, right? So in this case, how could we tackle those nonlinear sensor complexities? So to address this issue, my research groups has further developed two approaches. One is leveraging the deep learning, another is leveraging the kernel functions, kernel tricks. So here, this slide is highlighted some of our main ideas. So in particular, to tackle these complex relationships among the multiple sensors, so we used deep neural networks, try to automatically learn these relationships. And then in addition, instead of using this parametric mixed effect model to quantify the underlying degradation process, So we choose LSTM, which is flexible enough, right, to quantify the evolution of the trend. And then we develop algorithms, which is integrated back propagation algorithm that can jointly train these two models. So here shows the results, where this blue is our proposed new methods. And we compare these methods with several other like linear fusion functions. And it shows that once we consider this nonlinear fusion, indeed, it can further improve this RUL prediction results. So in addition to deep learning, we have also pursued another approach, which is by using kernel tricks. So the idea here is in our previous fusion function, we just consider a linear combination. And here we try to map this original X into a feature space. But actually the trick in the kernel is we do not need to know how to map this signal into feature space. As long as we know how to calculate the kernel, then that is sufficient, right? So this is called the kernel tricks. And we achieved very similar results when we consider the nonlinear fusion functions by using kernel tricks. And when comparing with those linear fusion functions, we can further improve the prediction accuracy by a large margin. So far, we have already studied a lot of those extensions. But then another question came to our mind because, as I mentioned, there are different sub-data sets available. But so far, we only studied the FD001. And in practice, the units may fail because of different failure modes, and also the unit may operate under different conditions. Like in this engine example, the engine can operate under different altitude, different pressures. So in this case, how could we extend our health index model? So here I plotted the engines fail due to two failure modes. One is fail in the fan, another is fail in the high pressure controller. So which is highlighted in this red and also the green color. And here the black shows the overlaps between these two failure modes. So what I want to show you is if we use each original sensor signal, those are all the plots for each original sensor signal except the last one. You can see that there is a large overlapping area, right, for the engines fail because of this two failure mode. So this means that we cannot effectively distinguish the failure mode. And this can lead to really poor RUL prediction results. So to address this issue, many research groups try to develop another fusion function tailored to this multiple failure modes. So here is some results showing that we can effectively separate these units, right, during the degradation process. And in this way, we can identify the failure mode, and it can lead to better prognostic results when we compare with one that does not consider this multiple failure mode. Similarly, we have also extended our model into the case when there are multiple operation conditions. So by constructing different health index models based on different conditions. But one challenge here is how could we make sure their degradation is a continuous process. So there is some additional efforts we made. Okay. So this is basically about this health index approach. After that, my group have also pursued some other like popular methods. One idea is we realize that in the health index approach, we start with the multiple sensor signal, and then we construct a health index, right? And this lead to our RUL prediction. But in practice, although the health index is highly desired, but if our goal is only in the RUL prediction, so can we start with the sensor directly have the RUL? So this motivates us to study more generic, those explainable machine learning and AI models. Here, I chose one of the representative papers with my former PhD students, Mihi Kim, who is currently assistant professor at the University of Florida. So the motivation here is based on our experience in the health index construction approach, we realized that One, the system has a very complex relationships, and one want to study a degradation of a complex system, then constructing the health index can be quite challenging. Especially, you see the FD004 data sets. There are multiple failure mode and multiple operation condition. And recently, the deep learning has shown to be a very powerful tools, right? And showing successful in a lot of those applications, including NLP or image classification. However, one deep learning has been applied to prognostics. In our view, there are often two limitations. First, they often only provide a point estimation for the failure time or the RUL. So without uncertainty quantification. But the uncertainty quantification is highly needed and desired in practice. Second, most of the times those deep learning based models behave like a black box. They are purely data driven, does not consider the property or the unique characteristics of the degradation. So what I mean here is often they just treat the multiple degradation signal as the conventional time series data, and then try to predict the future value without considering any domain knowledge. So that's why in this work, our goal is we want to provide deep learning based model, which is tailored to the prognostic need that can provide first high accuracy in the prediction. Second, it has a wide applicability. So what I mean here is we do not hope the model assume any particular type of degradation process. And also it does not need any specific knowledge such as existence of a failure threshold. Okay. And also we hope it can provide improve the practical interpretability, which reflects in the following two aspects. First is accurate uncertainty quantification of the RUR prediction. Second, it can incorporate those desired properties of the prognostic approaches. So in the following, I will talk into more detail how could we achieve this goal. Okay. So mathematically, we can formulate the problem as follows, right? Our goal is try to predict this RUL in the Y, and our inputs is a multiple sensor signal L. And we want to build such a neural network with a parameter W. Here we can use, here we didn't specify which particular neural network you can we use, and depends on different use cases. You can choose a different neural network. And here we will focus on the contribution in the framework. And based on this, we can derive the loss functions. You can see that this negative log likelihood actually includes two parts. One is related to the fitting of this model. Another is related to the uncertainty, like sigma squares. So this motivates us actually consider two types of uncertainties which exist in the prognostics. The first uncertainty is weight uncertainty. This is because we use a neural network model, try to fit the data, but only limited data available, right? So that's why there will be a model uncertainty exist, which is characterized by the W. The second type of uncertainty, we call it as degradation uncertainty. So this is mainly stems from the stochastic natures of the degradation process, which is captured by the sigma squares. And this is due to the system-to-system variability and also the signal measurement errors. And in this work, we try to effectively integrate both types of uncertainties. And in the following, I will start by explaining the degradation uncertainty. And our novel idea here is we imposed monotonic relationships with RUL when we handle this degradation uncertainty. So this basically means that as RUL decreases, we hope this degradation uncertainty to also decrease. Okay, here is the illustration. Assume when we conduct the degradation analysis in the initial stage. So in this case, you can see that there is no clear degradation trend. So when we conduct the prediction in the future, so it is very easy to understand and very easy that we have a large uncertainty band, right, in these RUR predictions. However, once we have more and more those degradation signal, and also as a unit approach to failure, in this case, the prediction become more critical. And in this case, we hope the uncertainty to be as small as possible, right? And how could we achieve this type of desired properties? Here, mathematically, we choose to use just a simple feed-forward neural network with a single hidden layer to achieve this monotonic relation. So we can model the log of the sigma squares, okay, with respect to this RUL prediction rate, RUL. And through these chain rules, okay, we show that if we force those parameters in this feed-forward neural network to be positive, then we can achieve these monotonic relationships. And how about the weight uncertainty? So here, our idea is to use Bayesian neural networks. So the difference between Bayesian neural network and a traditional neural network is in the conventional neural network, the weight parameter is a fixed number. But in the Bayesian neural networks, the weight parameters has a distribution. Okay. In this way, we can quantify the uncertainties. Well, this is theoretically sound, but the challenge really lies in the computations. For example, if we want to predict the future RUL for test units, right? Given we observe some degradation signal L, and in this case, we can expand this probability. And this involves a calculation of the posterior in this degradation, in this neural network weights. And this is, in most cases, this will be computational intractable. Okay, so to address this issue, one approach is to using variational inference. Okay, and here we used a Monte Carlo dropout, okay, to realize this variational inference. And mathematically, we can use these techniques to empirically estimate the mean and the variance of the predicted RUL. Okay, here I skip the detailed duration. But what I want to emphasize is if you look at this variance in the predicted RUL, it involves two parts. The first part is the uncertainty from the degradation process, the degradation uncertainty. And the second is uncertainty from those unknown parameter W. And here is our proposed framework, which highlights our like new idea and contributions. So assume that we have already collected some historical field units, right? Then based on those historical units, then we can use moving windows to construct different samples as inputs to this neural network. Then based on different moving windows degradation signal, then we can estimate what will be the RUL. And since we have already collected some historical field units, then we know the true RUL, and then we can plug it into the feedable neural networks to have output in the degradation uncertainty. And then we can jointly train these two parts. Okay, this is the offline training stage. During the online training, assume that we have already collected some in-field degradation signals. And then we can plug into this neural network to predict when this unit is going to fail, right? And based on these predictions, then we can use a Monte Carlo dropout to calculate what is our mean posterior values in the RUL. And this mean prediction RUL will be inputs into the feed-forward neural network to predict what will be the degradation uncertainties. And this will be, once this is available, then this will be an input to further calculate the uncertainties, calculate the variance in the predicted RUL, okay, during the online process. So in the following, I want to show you some studies, again, based on the CMAPS data sets. And here we considered all the full sub-data sets, okay? And here is the results. The first column shows our proposed methods. And the second column shows the method if we do not consider the monotonic constraints, okay, between the degradation uncertainty and the RUL. And all the remaining one are the alternative approach, okay, based on the deep learning based prognostics. So you can see that using our proposed method, indeed, we can improve the prediction accuracy by quite a large margin, right? And also adding this monotonic constraints helps to improve this prediction accuracy further. And here we plotted the predictions between our proposed method and the house index approach. And this can highlight more clearly about our method advantage. So you can see that in the FD001 datasets, where there's only single failure mode and single operation condition, what we can see is using our proposed new methods, we can well quantify this uncertainty, right? And also, if the unit proves to failure, which means the true remaining swirl becomes smaller, right? And our uncertainty indeed becomes smaller. This is actually because of the monotonic constraints. And we can also achieve a similar kind of observations even when we deal with this multiple failure mode and multiple operation conditions. But using the house index approach, as I mentioned, is really hard to construct and be successful in these complex scenarios. Again, after we developed this work, another question came to our mind is, how do we impose sensor selection in this case? This is actually one of the limitations in the neural network is we often use whatever provided or whatever available, right, to try to predict some response Y. But if there's a garbage in, then garbage out. So to address this issue, we further extended our efforts to develop adaptive sensor selection framework for the multi-sensor prognostics applications. So this means that our framework can adaptively select only the informative sensors at the moment to improve the RER prediction. So here illustrates our ideas. This is our deep neural networks, mainly this model that I showed in the previous slides. And our new efforts is actually shown here, where we try to regularize those non-informative sensors by using ReLU layer, okay? And then we try to jointly optimize the sensor selection and also the RER predictions together. But of course, there is additional R&D efforts needed because in order to prevent overfitting. So we further proposed several regularization strategies, such as a sensor dropout, sensor level dropout. This is a new concept. And also sensor disentanglement penalty and also selection variational penalties. And here you can see that although our deep neural networks methods that I showed in previous slides has already achieved amazing results, but once we consider the sensor selections, we can further improve the prediction accuracies greatly. Okay, this shows that really important that we need to screen out those noisy sensors. So far, I mainly talk about how do we conduct prognostics in like more those common applications. In the followings, I will focus on particular challenges is when we conduct prognostics with limited observations, but we have a large heterogeneous units. In this case, my research groups, we try to develop several transfer learning based techniques. And here is a motivation example. Assume that we look at a machine that they may associate with different working condition, different model type, and different manufacturing design information. So, but each unit only have a limited observation. So in this case, how to conduct prognostics? That is a long-standing challenge. One intuitive idea is we can model each unit individually. But the problem is we do not have sufficient data available to learn each individual model, right? Another approach is we can aggregate all the data together at the population level, and then learn some population characteristic model. But such a model cannot well explain the unique divulgation for each unit. So that's why to address this issue, one idea here is we try to numerically model the relationships among those unique covariates for each unit and the unique degradation coefficients. Okay. And once we build this link, then we can know the similarities among different units. Even we do not have any degradation signal, just purely based on their covariates. And also we can update this similarity estimation if we have more and more those observations. So our particular technical approach by using multivariate Gaussian process. Okay. But one unique advantage we found in this type of approach is traditionally, if we collected some sensor signal from unit 1, then we can only update the RUR prediction for unit 1. But here, since we can numerically quantify the similarity between different units, so once we collect some data from unit 1, then it's also possible to transfer such knowledge into another units and update its RUR prediction results, even though we do not have a new observation from this unit. Okay, this is a very unique advantage we see. And here shows some numerical results. And here we consider a real case study based on the ADNI data sets, which is a study studied the disease progression for Alzheimer's disease patients. And here you can see that once we consider the transfer learning approach, it can better predict the disease onset and the evolution comparing with other alternative methods. Because now we can quantify the kind of similarity between those patients based on their risk factors. Okay. Once we have a better prognostic results, then my group have also studied some decision-making models. So due to time limits here, I just briefly talk about it. So one idea here is we propose a dynamic workload adjustment strategy, try to prevent the overlaps among the machine failures, maximizing the throughputs. So you can see that if many machines suddenly fail, then the remaining one cannot satisfy the production anymore. However, we know that the degradation of a machine highly dependent on the workload assigned, right? So the higher the workload, then the quicker the machine is expected to fail. So this means that we can online adjust the workload assigned to those machines, right, in order to control the degradations of those different units. So here we proposed one techniques and try to achieve this goal. In addition, we have also studied some adaptive maintenance strategies, try to online update the preventive maintenance schedule based on the real-time machine ages and also the RUL prediction results. Our goal is try to minimize the total cost, including like the tarnish cost, preventive maintenance cost, and also corrective maintenance cost. Okay. So in summary, during this talk, I mainly talk about three general approach when we conduct prognostics, including start with the health index and methods. And then I talk about those explainable machine learning and AI models. So for those models, the goal is we want to develop a very generic approach with multiple sensors as inputs and RUL as outputs. But the challenge here is how could we incorporate those domain knowledge? And also how could we deal with those complex situations like sensor selection or even some sensors when they are asynchronized. And then I talk a little bit about how could we tackle those limited observations when we conduct prognostics in a heterogeneous units by using transport learning. And in the end, I briefly talk about some decision-making models. Okay. So here are the three main works that I highlighted today in this talk. And this is a publication list among those works that I just mentioned before. Okay, so far in our groups. So in the end, I want to quickly acknowledge the funding support from different funding agencies and also a group of, particular for this prognostic work, and also the group of students working in my lab. Okay, thank you. Any questions?
Yeah, thank you. Thank you, Professor Liu, for bringing us a very fruitful journey about data advances in prognosis, including the modeling, transfer learning, and decision making. Yeah, I personally really enjoy your talk, and thank you so much.
Thank you.
And I think we're open for questions and discussions. So for all the audience, if you have any questions, you can directly unmute yourself. And I think Dr. Liu is also happy to discuss with all the audience.
Hello, Dr. Liu.
Hello.
I'm Zihan. Yeah, I'm Zihan, and now currently working with Dr. Kim. Could
Oh,
I like have two brief questions?
sure.
Yeah, like could we going back to page 34, please?
This one?
Oh, yes. So, here I'm like confusing about like for the degradation uncertainties, do we still consider like the underlying degradation process as a stochastic process or is still parametrically?
Yeah, here we do not impose the parametric assumptions in the underlying degradation model. So here the like uncertainty mainly because of the stochastic natures, but we do not impose any parametric like degradation model like in the previous house index cases.
Yeah, so because we consider it's like a stochastic process, and one property we might need to consider is like is a stochastically independency between like each time unit. So, for a neural network generated process, how could we like enable like for the each times series based remaining useful life is like stochastically independent.
Okay. I think this is a great questions. And here, I think because the goal, I think the question you mentioned is more related to the modeling the evolution, right, of the sensor trends. In this case, you want to have some Brownian motion, those type of assumptions. But here, remember, we do not try to model the evolution of the signals. We just directly predict the RUL. So that's why the problem is a little bit different.
Okay. Yeah, I
Right.
got it.
Yeah.
And could I like have a more like a general question? Like I know like for this project, the house index is not involved, but like I'm wondering for what kind of condition we should consider to use a house index and for what kind of condition we do not need the house index.
Yeah, I think this is a really great questions. I think a health index in general, that is a very easy, like understandable, like metrics and highly desired by practitioners. So my suggestion is also depends on the use cases. So if the use cases is not very complex like here, and when you work with industry, then the health index approach, I will say it is desired. But if the goal is different, just want to get a better RUL prediction results, and you don't care about the visualization, you don't care about those underlying like interpretations about the degradation evolution, then I will say the deep learning based approach indeed we see it has the best performance so far. So performance wise, this will be I think more powerful. But from the interpretability perspective, the house index is more powerful.
Yeah, thank you, Dr. Liu.
Yeah, you're welcome. And good luck with your PhD.
Yeah, thank you. Thank you
Yeah.
so much.
Yes, is there any other questions? Yeah, maybe I have a general question. So,
Sure.
yeah, I see from your the whole talk, mainly you focus on the soft failure. Do you see any like opportunities or challenges by extending those type of works to the hard failure cases.
Okay. So soft failure here, you mean more like we assume
Like
there
you
is
have a
like a
predefined,
threshold.
you have
Okay.
threshold, even if the unit didn't fail in practice, but once it touched the threshold, you deem it as a
Right.
hard
Right.
failure means you
Right.
like you run the unit until it doesn't function, right?
Yeah. So I understand. Just want to make sure we are on the same page before answering.
Sure. Yeah.
Yeah, I think in the house index-based approach, we mainly rely on this like soft threshold assumptions, as you mentioned, because we need some kind of like I would say like a domain knowledge to somehow guide how to construct such a house index, right? Make it more interpretable. But for those deep learning based approach, you can see that we do not impose such soft threshold constraints. This is one of the motivation why we want to directly predict the ROM. So how to combine these two? I think maybe I think I also learned something from what Zihan asked. Maybe there is a room that we can combine both approach and together. Actually, recently Professor Shi Yuzhou and I, we have a new project funded by ONR. And one of the idea is we try to build a health index as an intermediate layer before we throw it into the deep neural networks. In this way, we try to maximize the advantage of both parts. And hopefully, I have some more work to present maybe in the future.
Okay, thank you. So hopefully we can invite you again once you have some progress and updates for that part. Yeah.
Sure. Yeah.
Okay, any other questions from the audience? Yeah, if not, I think I just want to represent all the audience to thank you, Dr. Liu, for this wonderful talk again.